All right, so today we're going to talk about energy and states of matter. And we're going to start by showing these notes that I wrote down during class recently here. I meant to make a recording of this and I didn't, so I'm just going to kind of point at a few things through here. And then if you don't have these notes, you'll be able to get these. So this is a graph showing the icy hot lab, which is the boiling ice lab, as we did in class. And so this is just kind of my scratchy indication of what the data looked like, and the idea that for a long time while the ice was melting, the temperature did not change in any kind of a major way. It changed just by a degree or two, really, during this time. And then right about the time that the ice was all melted, the temperature started to increase at a pretty straight, steady pace. And then right about the time that the water is sort of starting to boil and steam is starting to come out, you have the temperature starting to increase less and less and less until finally, as it gets really close to the 100 degrees boiling point mark, then there's really no appreciable change in the temperature, because as that water is boiling, it's changing into steam there. And so we also talked about the idea that we're adding thermal energy right here, that time is what we're graphing because that's what we were really measuring. But the significant thing here is that we were adding thermal energy throughout this whole entire time because the beaker of ice was sitting on the hot plate, meaning that thermal energy was going into the beaker. So then we talked about this very important question here about what is happening to the energy and to the particles in these different situations. So at the time when the temperature is rising, it's pretty easy to see that the particles are increasing in their speed. That's what a temperature increase means. We also know that the thermal energy is increasing because, in fact, we are adding the thermal energy, just like we talked about here. But there's a little different situation when the temperature is constant, right? During this time here where the ice is melting. The temperature is constant, which means that we know that the temperature is not increasing because it's not going up. But we also know that thermal energy is being added because we're sitting that thing on that hot plate and the energy is going into it in that way. So the energy, therefore, has to be doing something other than making the water warm up, making the particles move faster. And so what we talked about happening is that we're breaking some intermolecular forces between the particles. The forces, there's a lot of different kinds of intermolecular forces, inter being between, and molecular, of course, is molecule. So particles, this is really just the forces between the particles. And so there's a lot of these different kinds of these, and you can learn about those as you study more chemistry in the future. But there's these forces that hold the ice into this crystalline form, right? And then there's kind of a similar but less kind of a structured idea that is holding the particles of water together into a blob and preventing them from sort of jumping out and becoming the gas, right? And so that's what's happening during this time when the ice is melting, is that the energy is working on breaking those things right there. When that energy goes in and the energy is being absorbed kind of in that format right there, we call that phase energy, contrasting it with the idea of adding the thermal energy, like up here, like, right, we have different kinds of energy. So that's those notes right there, and you can make sure that you get those down also. All right, so to continue this discussion for today's notes, we're going to talk about, like I said, we're going to talk about energy and states of matter. Okay, so energy is a kind of a funny idea just because we talk about energy in kind of vague terms sometimes. But what we want to talk about today is we want to talk about how energy can be in different forms, right? So we've already talked about, you've learned a lot about in your life at different times about kinetic and potential energy. Another kind of energy that we've talked about a good bit here is chemical energy. And so you can think of this as energy that holds together particles. Maybe you could even put the word molecules in there, right? You have different atoms that are held together that way. And so when we talk about rearranging the particles in a chemical reaction, rearranging the atoms in a chemical reaction, you're changing the way that the chemical energy is distributed, and sometimes it gets released or absorbed. The other kind of energy that we've talked a lot about already is thermal energy. And so this is the energy of particles moving. And so we talked about the idea that a greater thermal energy is correlated with faster particles. Today, this other idea that we're adding in for this unit here is this idea of phase energy. And so this is the energy that holds the structure of a sample together well, maybe I should say, let's say it holds the structure of particles together. So for example, you've got a solid, right? And those particles are all attracted to each other. So that would be the phase energy holding them together. You've also got particles of a liquid, which are much less connected, right? They can move around a lot. Kind of showing some motion here. But ultimately, they're very, very closely associated. They don't go anywhere away from the other particles. And then you've got the idea of a gas, right? And these are moving at a very fast rate. And they're substantially further apart, probably even more further apart than I've kind of drawn them here in my tiny little picture. And there's really no appreciable forces that are holding those structures together. So that's the idea of the three kinds of energy that are important right now. Another aspect to throw into this would be just to talk about which of these has the highest amount of phase energy. And this would be the highest over here. And this would be lowest, with the reason being that the amount of energy that it would take to break these, you could add energy in order to break those. So the energy is not tied up so much in holding them together, okay, as kind of almost the reverse of holding them together, right? If you add the energy, then these very natural attractions will break. And then if you add energy to this, if you add phase energy to this, then it will break the attractive forces between the particles and allow them to kind of float freely into the air in that kind of a way. All right, so the next thing that we're going to do is we're going to talk about how energy transfer can happen here. So we're going to talk about this situation here of a melting ice cube. And so we're going to kind of start with this kind of an idea right here and end with the well, I guess we'll really just do one change right here. And so we'll have the idea that we have energy that's thermal energy and energy that's phase energy. I'm not going to draw the chemical energy today because it's not going to matter. We're not going to do any chemical reactions. We're just going to take an ice cube and melt it. Starts out as water, ends as water, so no chemical change is happening here. Okay? And then we'll, of course, have the same energy types at the end. Okay? With a change here. So what we're going to talk about here is this idea that when an ice cube starts out, how much energy would it have? Well, it's cold, right? We typically use 2 bars of thermal energy to represent room temperature. So I'm going to draw just 1 bar of thermal energy to represent a cold ice cube. Okay, I should probably put this in here, melting ice. Okay, we also routinely use 1 bar of phase energy to represent any solid. Okay. And then 2 bars would be a liquid and 4 bars for a gas because it takes a lot of energy to make a gas. All right, so this is how we would start, right? It's cold. It is a solid, okay? We have this kind of a molecular arrangement going on right now. And here's our ice cube. You don't always have to draw in here, but it's kind of maybe helpful to think about. There's our ice cube, okay? So what we're going to do is, in order to melt the ice, we have to add energy to it. All right, so we have to do something to warm this thing up. Typically speaking, thermal energy is the only kind of energy that you can add to a system. It's the kind that we sort of have that's easily flowing around in our environment, right? It's very easy to transfer thermal energy. So what we kind of can think of is whenever we make an energy transfer here, we always transfer energy that's thermal energy, and then thermal energy can become phase energy. So what I'm going to do here is I'm going to show you, we're going to put energy into the system, right? So the first thing we're going to do is warm it up. So let's warm this thing up. So here's 1 bar of energy that we can add into here. All right. We're adding some thermal energy. And when we do that, we would end up with here we go, with 1 bar of thermal energy, would be increasing this to 2. But what we really need to do here is we need to melt the ice. And so we need to warm this up in order to be sort of more, well, this is where really there's 2 different ideas, 2 different options here, because I didn't put an ending temperature on here. So we'll just talk about both the ideas. The first option is we could just leave it like this. And we can say, well, the thermal energy goes in. There's the 2, right? But then really what happens is that this one doesn't actually stay here. It actually jumps over, kind of LOLOL style, but we're just going to draw it with this simple chart today. Okay, and then it becomes that. But it's still cold, right? Because we still have just the 1 bar here of thermal energy. So this would be how you draw this if the sample stays cold. If the sample warms up, right, because you can have cold water or you can have warm water, right, we could add more energy to the system. I'll draw it with a different color so you can kind of see this happening here. We could add 2 bars of thermal energy. And if we add 2 bars of thermal energy, one of them will go into making this a liquid, just like this one did. And the second one will make this warm up. So now I'm kind of wishing that I didn't draw that X there. So I'll just do the best that I can there. Do you see that? So the first option was that you keep it being cold, right? Right? Sample stays cold. Because the thermal energy didn't really increase to speak of. We stayed at 1 bar and 1 bar. And then the second idea was saying that the sample also warms up. And so that way we would have an increase in thermal energy and also an increase in phase energy. The last thing that I want to add in today is just a couple of vocabulary terms. Okay, so this is the first term right here is called heat of fusion. And this is just simply the amount of energy. Now I'm going to say specifically the amount of phase energy. Required to melt. And really this would go the other way too. You could also use this same amount of energy, if you removed it, to freeze. A liquid without also changing its temperature. So what that really means is this is a specific quantity, and we could actually measure it. We would use joules to measure it because that's a unit of measure we use to talk about measuring energy. And so we could actually measure how many joules of phase energy was equivalent to our sort of conceptual size of 1 bar of energy. And that would be very specific to the amount of phase energy that's in 1 bar of phase energy, which would not be the same as whatever energy is in the bars of thermal energy that we're using to increase the temperature of something, right? Temperature is what changes when you change the thermal energy, but phase energy, when you add or subtract phase energy, presuming you add or subtract enough of it, then that's when you melt or freeze the liquid. Okay? Then the second term is the heat of, we call it vaporization. I bet you can guess this one. This is the amount of phase energy required to boil or condense a liquid, also without changing its temperature. So kind of in a similar way, this would be talking about what it means to convert the liquid into a gas, or to likewise do the reverse and convert a gas into a liquid by condensation. So those are the two terms that you need to just kind of be aware of, that they exist. And the next place that we'll go in chemistry after this is to talk about how to actually calculate these amounts. And there's things that you can do to actually calculate these amounts. But for now, this is all you need to see.